Okay, in this video we're going to be looking at how to estimate a population standard deviation or variance. We're still on confidence intervals, so we're finishing up this part on confidence intervals by estimating a population standard deviation or variance. Alright, so in this case we're going to be looking at a point estimate. We're going to find out what the best point estimate for a population variance. So in this case here, it's going to be the sample variance. So the sample variance, or S squared, would be the best point estimate of the population variance, which is in this case sigma squared. Okay. So for the population variance, the best point estimate will be the sample variance, and you could probably guess that the sample standard deviation is going to be commonly used as the best point estimate of the population standard deviation, although it is a biased estimator. So in this case, we'll say that the sample standard deviation which is S, that will be the best point estimate of the population standard deviation. Which is in this case sigma. Okay, but keep in mind that sample standard deviation, it is a biased estimator. Well, the population standard deviation is a biased estimator, and it does have a small bias. Okay. Now the next thing we're going to talk about, now when we're estimating a population variance or a population standard deviation, the distribution that we use is a chi-square distribution. For a population proportion, we use the normal distribution. For a mean, we use the t-distribution or the student t-distribution when sigma was unknown. Now in this case, when we're estimating a population standard deviation or a population variance, we're going to be using what they call the chi-square distribution. Okay? And this is the Greek letter chi. And it's squared, so we do have the exponent of 2. Okay? Now that sample statistic has a sampling distribution which is called the chi-square distribution, and then that's going to be equal to n minus 1 times s squared divided by sigma squared. Okay. Now later on in this course we will be using that particular chi-square distribution, and in this case your n, that's your sample size, s squared is the sample variance. Now if you're given the sample standard deviation, you take your sample standard deviation and square it. And then sigma squared population variance. Okay. Now in that case, if you're given the population standard deviation, you'll take that population standard deviation and just square it. Okay. And this is an illustration of what the chi-square distribution looks like. It's actually not a normal curve. It looks somewhat like this. So in this case here, when we're finding critical values, we're going to be finding two of them. There'll be one on the left and the other one on the right. Okay, and I'll shade in the area in green on the left and on the right. You're going to be finding two of them. One is the chi-square value on the left-hand side, and there's another chi-square value that you'll find, and it'll be on the right-hand side. So those are the notations for chi-square on the left and chi-square on the right. Okay. And to find those chi-square values, we're going to be using table A-4. And table A-4, for those of you who are not in my class and just watching this, is the chi-square distribution table. Okay. Okay. Now, this is what the chi-square distribution table looks like. On the far left-hand side, you do see your degrees of freedom. And then you have decimal values at the top row. Okay. Now, those decimal values represent, and this is very important, the area to the right of the critical value. So we're dealing with the cumulative area from the right. In the other tables, like the normal distribution table, you were dealing with the cumulative area from the left. These decimal values here represent the cumulative area from the right. So in other words, if we're going to find the chi-square value on the right, we have to look at this area on the right-hand side. Now for the chi-square value on the left, is that area to the right, and not this area that's on the left-hand side. Okay? Because if you're given this area on the left-hand side, then you'll have to do 1 minus that area on the left to get the area on the right, because that table, that chi-square distribution table, gives us the area to the right of that critical value. Okay? And also, don't forget about degrees of freedom. We talked about that when we were doing the confidence interval estimate for a mean. That degrees of freedom is always your sample size minus 1. Okay? That's the number of sample values that can vary after certain restrictions have been imposed. Okay? So again, the degrees of freedom will be n minus 1. So on the table, you do have your degrees of freedom column on the left-hand side. Okay? And again, you have to use a conservative number if your degrees of freedom is not in that table. Okay, now let's look at some properties of a chi-square distribution. One of them is the chi-square distribution is not symmetric. With the normal distribution and the student t distribution, they were symmetric. In this case, the chi-square distribution is not symmetric. And then second, the chi-square values can be 0 or positive, but they can never be negative. So your chi-square values will never be negative. Okay. And the third is this. The chi-square distribution is different for each number of degrees of freedom. So as the number of degrees of freedom increases, the chi-square will be approaching a normal distribution. So in this case here, this is what the chi-square distribution looks like. You can see that it's not symmetric and all the values are non-negative. And then on the right side, you'll see what the chi-square distribution looks like for 10 degrees of freedom and what it looks like for 20 degrees of freedom. Okay, and because that chi-squared is not symmetric, the usual format for a normal distribution for a proportion and for a population mean do not apply. So we can't use s squared minus e, which is less than sigma squared, and less than s squared plus e. Okay? So we have to use separate calculations for the upper and the lower confidence interval limits. Okay? And that's where table A-4 comes in. Now this is very important. As I talked about earlier in table A-4, each critical value of chi-squared in the body of the table corresponds to an area given in the top row of the table, and each area in that top row is the cumulative area to the right of the critical value. Cumulative area to the right when we're dealing with table A-4, which is that chi-square distribution table. Okay. So now let's look at how we can construct a confidence interval estimate. So we're talking about a confidence interval estimate for, I'm going to say sigma, which is your population standard deviation, and sigma squared is going to be your population variance. Okay. In this case, there are two requirements to do this. Number one, you must have a simple random sample, meaning that samples of the same size has an equal chance of being selected out of that population. So you must have a simple random sample. And number two, and this is very important here, the population must have normally distributed values. Okay, this is a very strict requirement. So that means departures from the normal distribution can result in large errors. It's very strict, and it's very important that the population must have values that are normally distributed. Okay. Now, let's talk about the format for the confidence interval estimate. And I'm abbreviating this CI for a population variance. And that's sigma square. It's going to follow this format, n minus 1 times s squared, and that's divided by the chi-square value on the right, and that's less than sigma square and less than n minus 1 times s squared divided by the chi-square value on the left. And it is correct for this to look like this. Okay. So that's the confidence interval for a population variance. But for a standard deviation, we just simply take the square root of this compound inequality, because we know for a population standard deviation, you just simply take the square root of the variance. So here's your confidence interval for a population standard deviation. Or just simply sigma. So we just take the square root here. So the left side will be the square root of n minus 1 times s squared, all divided by the chi-square value on the right, and that's less than just sigma and less than the square root of n minus 1 times s squared divided by the chi-square value on the left. Okay. This one we'll use. This is for population standard deviation. The one on top represents the population variance. Okay. And there is a round-off rule that you need to be familiar with. If we're using an original set of data values, then you're just going to construct the confidence interval, round the confidence interval limits to one more decimal place than used for the original set of data. Okay, so if your data values were all whole numbers, then you'll round your limits to one decimal place. But most likely we'll be using summary statistics, your sample size and the sample standard deviation, N and S. In that case, you'll round your confidence interval limits to the same number of decimal places used for the sample standard deviation. So if the sample standard deviation is like to one decimal place, then you'll round those limits to one decimal place. Okay, and this next thing we'll pull up here is the procedure for constructing the confidence interval estimate for the population standard deviation and the variance, population variance. Number one, verify that the two requirements are satisfied, and then you're going to be using n-1 degrees of freedom, either use technology or refer to table A-4 to find the critical values. So here you got your chi-square value on the left and the chi-square value on the right that you're going to find that will correspond to the desired confidence level, and then evaluate the upper and lower confidence interval limits using this format. Now, if we're dealing with a population standard deviation, which is just sigma, then you just take the square root. And then finally round the resulting confidence interval limits using the round-off rule that I just got through talking about. Okay, so let's look at some examples of constructing a confidence interval estimate of a population variance or population standard deviation. In this case here, use the given information to find the number of degrees of freedom, the critical values chi-squared left and chi-squared right, and the confidence interval estimate of sigma. It is reasonable to assume that a simple random sample has been selected from a population with a normal distribution, so both requirements have been met. Okay? And in this case here, we're dealing with nicotine and menthol cigarettes. 80% confidence, the sample size is 28 and the standard deviation is 0.24. Okay, so what I'm going to do here is draw the chi-square distribution, because it's not a normal curve, it's a chi-square distribution that we're dealing with. %, confidence means that the 80% is here in the middle. Now, in this case, if this is 80%, the area underneath that curve is 100%. The remaining has to be 20%, split evenly, meaning that this area on the left side is 10%. This area right here is also 10%. And that makes up the whole 100%. Okay. So now let's first find our degrees of freedom. That's n-1, which is 28 minus 1, or 27. So our degrees of freedom is 27. And we have an 80% confidence level 99% confidence level. So from here we can find the chi-square value on the left and the chi-square value on the right. Okay. Well, the chi-square value on the right is easy to find. This is your chi-square value on the right. Now keep in mind we're dealing with the cumulative area on the right for both chi-square values here. So for chi-square value on the right, the area to the right is 10% or 0.10. Now for your chi-square value on the left, we want this area to the right. So if this is 10%, this area to the right must be 90% or 0.90. So using table A-4, or your chi-square distribution table, we're going to find 27 degrees of freedom, which is down here. And then look at the top for these two values. 0.90 is right here, and also 0.10, which is here. Okay, that 0.90 represents the chi-square value on the left. The 0.10 represents the chi-square value on the right. So for 0.90 and 27 degrees of freedom, here's 27 degrees of freedom. For 0.90, that's going to be 18.144. So your chi-square value on the left is 18.144. Now, your area to the right of the chi-square value on the right is 0.10. So find 0.10, and again, 27 degrees of freedom, which is right here. So 27 degrees of freedom and 0.10 will be 36.741. Okay, so those are my chi-square values on the left and on the right using table A-4, or the chi-square distribution table. Okay, I have those, and I know what n-1 is, and I know what s is, which is just standard deviation. I can use the format for the confidence interval for a population standard deviation, which is just the square root of n-1 times s squared. Oh, that's divided by the chi-square value on the right. That's less than sigma, and less than the square root of n-1 times s squared. Oh, that's divided by the chi-square value on the left. And all I do here is just substitute those values into this formula. Well, n-1, that's what, 28 minus 1, which I found that out to be 27. So I can just substitute that n-1 with that 27 times s in this case is 0.24. I might as well write this out as s is equal to 0.24. So we'll substitute 0.24, but that has to be squared because it's just a sample standard deviation. S squared, take that and it's just squared, 0.24 squared. Divided by your chi-square value on the right will be 36.741. That's less than sigma and less than the square root of. The numerator is exactly the same. So it'll be 27 times 0.24, that's squared, divided by your chi-square value on the left. That's 18.144. Okay, so just go ahead and calculate that. Using our calculator. Okay. marginal. Okay. Now on the left side, we do second x squared, and then 27 times 0.24, and then hit x squared to square that, and then divide that by the 36.741. Close parentheses. Then hit enter. Okay. Now our sample standard deviation is to 2 decimal places, so we need to round this off to 2 decimal places. So 0.205 will be 0.21. So this is 0.21 on the left-hand side. That's less than sigma and less than. Okay, we do the same thing on the right side. Second x squared. 27 times 0.24. You square that. This time it's divided by 18.114. Close parentheses. Hit enter. To 2 decimal places, that would be 0.29. So this is your confidence interval estimate for a sample standard deviation. Well, for your population standard deviation. So in this case, that's between 0.21 and 0.29. Meaning this. We are 80% confident that the true standard deviation of the amount of nicotine in menthol cigarettes falls between 0.21 milligrams and 0.29 milligrams. Okay, so we're dealing with the true standard deviation of the amount of nicotine in menthol cigarettes. Okay, take a look at this next example. In this case here, we're dealing with platelet counts for women. Okay, so we're going to use that same given information. Well, we're going to use the given information and find the number of degrees of freedom, the critical values, both chi-squared left and chi-squared right, and the confidence interval estimate of sigma. Again, it is reasonable to assume that a simple random sample has been selected from a population with a normal distribution. Both requirements have been met. Okay, so let's look at what we have here. The platelet counts for women, we're dealing with an 80% confidence level. Sample size is 23. Your sample standard deviation is 65.1. So in this case here, we have our degrees of freedom. That's n minus 1. N is 23, so 23 minus 1 will give me 22. So I have 22 degrees of freedom. And we're dealing with an 80% confidence level. %, confidence means we need a chi-square value on the left and a chi-square value on the right. And it helps to draw a chi-square distribution curve that looks like this. 80% is in the center, so that tells me that this must be 10%. This is also 10%. Both of these tails are split evenly. Okay. So here we want to find our chi-square values on the left and the chi-square on the right. Okay. The chi-square on the right is quite easy because the area to the right is just 10% or 0.10. But for the chi-square value on the left, that's this area to the right. 80 plus 10% is 90% or 0.90. Okay. So now, let's use table A-4. Okay, we're using 0.90 and 0.10, but this time with 22 degrees of freedom. So here's 22, and we read across with for 0.90, that's going to be 14.042, and for 0.10, that's 30.813. Okay, so the chi-square value on the left, that's your 14.042, and 30.813 represents the chi-square value on the right. And from this, we can find our confidence interval estimate for a population standard deviation. And I'll go ahead and rewrite the formula. Okay, that's square root of n minus 1 times s squared divided by chi-square right less than sigma and less than n minus 1 times s squared divided by chi-square on the left, and all that's underneath the square root symbol. Okay, n minus 1 is 22. So we got the square root of 22 times, and of course s, that's 65. If you recall, so it'll be 65.1, but that has to be squared because we're given the standard deviation, not the variance. So we take the standard deviation and square it. The chi-square value on the right is 30.813. That's less than sigma and less than the square root of. That numerator is exactly the same, 22 times 65.1, and that's squared, divided by, now your chi-square value on the left is 14.042. Now in this case, we do the square root of 22 times 65.1 and then squared, divided by 30.813. Close parentheses, hit enter, you're going to get 55.0. Because our standard deviation is rounded to 1 decimal place, so we round our limits to 1 decimal place. So that's 55.0, less than sigma, and less than. Now for the upper limit, second x squared. Let's see, 22 times 65.1 and u squared divided by 14.042. Close parentheses, hit enter. To 1 decimal place, that'll be 81.5. Okay. I'll just bring that over so you can see what I did here. So that upper limit is 81.5. So this is your confidence interval estimate for a population standard deviation. So if we were to interpret that, we can say that we are 80% confident that the true standard deviation of platelet counts of women is between 55.0 and 81.5. Okay. All right. Let's look at another example. Okay, now here we're dealing with a different confidence interval estimate. Here we want to use the given confidence level and sample data to find the confidence interval for the population standard deviation. Assume that a simple random sample has been selected from a population that has a normal distribution. And we're dealing with the salaries of college graduates who took a statistics course in college. And we want to construct a 99% confidence interval with a sample size of 31. The sample mean is 64,500 and the sample standard deviation of 18,218. Now, really, we don't need the sample standard deviation, because all we're going to be dealing with is just the sample standard deviation and constructing one for the population standard deviation. So we don't need the sample mean of x bar being 64,500. Okay, now degrees of freedom. That's n minus 1, or 31 minus 1, which is 30. Now we got a 99% confidence level. So here we want a chi-square value on the left and a chi-square value on the right. And on the far right, I'm going to go ahead and draw my chi-square curve. In the middle is 99%. Okay, now if that's 99%, the whole curve is 100%. Take 100% minus 99%, it's going to be 1%, or 0.01. But we got to split 0.01 into two parts, two equal tails. So 0.01 divided by 2 will be 0.05. So this represents 0.05. I'm sorry, 0.005. And this also represents 0.005. Okay. Alright. So we want the chi-square value on the right. Well, that area to the right is 0.005, but for the chi-square on the left, the area to the right will be 0.99 plus that 0.05, which will be 0.995. So using table A-4, or the chi-square distribution table, we're going to be using 0.995 and 0.005, which is off to the far right. And this time our degrees of freedom was 30. So we had 30 degrees of freedom in this case. So here, 30 degrees of freedom. There we go, 30 degrees of freedom at 0.995. That's going to be 13.787. So in this case here, that chi-square value on the left is 13.787. Okay. Now that same 30 degrees of freedom, but this time we're going to go all the way to the end to 0.005, which will be 53.672. So your chi-square value on the right is 53.672. Okay, so now we got our chi-square critical values on the left and the right, and we know the sample standard deviation, that's $18,218. We can construct our confidence interval estimate, which would be the square root of n minus 1 times s squared. All that's over the chi-square value on the right. That's less than sigma and less than the square root of n minus 1 times s squared divided by the chi-square value on the left. Okay, and just substitute those values. N minus 1, that's your degrees of freedom. N minus 1 was 30, so we can just substitute n minus 1 with 30. So that's 30 times s is 18,218, and that's going to be squared, divided by your chi-square value on the right, which is 53.672. And all of this is underneath the radical, by the way. That's less than sigma and less than the square root of, the numerator is exactly the same, so I'll just copy that over. 30 times 18,218, and that's squared. The chi-square value on the left, which is your denominator, that's 13.787. And then, then we use our calculator to get those upper and lower limits. So second x squared for the square root, and then 30 times 18,218, and that's squared, divided by 53.672, close parentheses, hit enter. You'll get 13,620.32, but here the standard deviation of that sample is a whole number. So we round to the nearest whole number. So this will be 13,620. So your lower limit is $13,620. That's less than sigma and less than. We do the same thing on the right side. Second x squared, 30 times 18,218, and that's squared, divided by 13.787, close parentheses, hit enter. We're going to round this off to the nearest whole number as well. That'll be $26,874. Now, to interpret this, we can say that we are 99% confident that the true standard deviation of salaries of college graduates who took a statistics course in college is between $13,620 and $26,874. Okay, last example. A chocolate chip cookie manufacturing company is recorded the number of chocolate chips in a sample of 40 cookies. The mean is 22.32, and the standard deviation is 2.78. And here we want a 98% confidence interval estimate of the standard deviation of the number of chocolate chips in all such cookies. Okay? So in this case here, we're given a sample of 40 cookies. And we're told that the sample mean, which is not needed, in this case is 22.32, and the standard deviation, S, that's 2.78. And we want a 98% confidence interval estimate. Well, in this case, your degrees of freedom, n minus 1, or 40 minus 1, which will be 39. So we got 39 degrees of freedom, and we're dealing with a 98% confidence interval estimate. So we need our chi-square value on the left and the chi-square value on the right. Okay, if I draw my curve for the chi-square distribution, 98% is in the middle, which means the rest of the curve is 2%. That has to be split into two equal parts. So this part on the left is 1%. This part on the right is also 1%. Okay. So, chi-square value on the right, that's the area to the right, which is going to be 0.01. And then chi-square value on the left, we have to consider the cumulative area to the right of that. 0.98 and 0.01 will give me 0.99. Okay? Because if this is 1% on the left side, the rest of the area on the right-hand side must be 99% or 0.99. So we're going to be using 0.99 and 0.01 in our chi-square distribution table, or table A-4. Now we're dealing with 39 degrees of freedom. So here we're going to be looking at only 0.99 and 0.01. Okay, so now for, well, 39 degrees of freedom is not on here, so we'll have to use 40 as a conservative number. Okay, so here's 0.99, that's this column here. And let's use 40. That's going to be 22.164. So your chi-square value on the left will be 22.164. Now for the chi-square value on the right, here 0.01 is this column right here. And 40 degrees of freedom, we're going to be using 63.691. Okay, so your chi-square value on the right is 63.691. Okay. Now we can construct our confidence interval estimate for a population standard deviation using the square root of n minus 1 times s squared all over the chi-square value on the right. That's less than sigma and less than the square root of n minus 1 times s squared divided by the chi-square value on the left. Okay, now n minus 1, which was 40 minus 1, which was 39, so we got the square root of 39 times, your s is 2.78, so we're going to do 2.78, and that's squared, all over the chi-square value on the right, which was 63.691, less than sigma, and less than the numerator, the square root of the numerator, which is the same, 39 times 2.78 squared, over the chi-square value on the left, 22.164. So here's where we use our calculator for this. For that. Second x squared for the square root. And then 39 times 2.78, and then you hit your x squared button, divided by 63.691, close parentheses, hit enter, you'll get, now we're going to round to 2 decimal places. The reason being is because our sample standard deviation is to 2 decimal places. So this will be 2.18 for our lower limit. Okay, 2.18. And that's less than sigma, and less than, and on the right side, second x squared, 39 times 2.78, and you hit your x squared button, divided by 22.164, close parentheses. To 2 decimal places, this will be 3.69 for your upper limit. So here, this will be 3.69 here. And that's going to be your confidence interval estimate for a population standard deviation. And if we want to interpret this, we can say that we are 98% confident that the true standard deviation of the number of chocolate chips in all such cookies is between 2.18 and 3.69. Okay? And hopefully this will assist you with the homework problems that deal with the confidence interval estimate for a population variance or a population standard deviation. And that will conclude this video on just that particular lesson.